Okay. Thank you everybody for to be here in our monthly seminar series. Um, Today we have two presentations from Alexander Bonilla and Andrés Lizardo. Both of them are going to speak about more theoretical formalism in gravitational waves. Some two announcements. We have only two announcements. One for the first call on gravitational wave in astrophysics in La Serena, Chile. They have no already website yet. And the second Latin American Conference of Gravitational Wave in Mexico. In this case, I don't see to Fabian, if Fabian wants to speak about this, but there is not so much advance at the moment, but we will have any information for the next month. Okay, then I have to present to Andrés. Now, Andrés, you can share your screen, please. And I will to present
Yes.
you. Pablo Andrés, he earned his PhD in physics from the University of Zacatecas. As a researcher, he specialized in cosmological data analysis, combining insights for traditional sources like supernovae, cosmic chronometers, and gravitational wave lensing. Recently, he has integrated gravitational waves into his research framework, aiming to bring theory and observation in modern cosmology. So now, Andrés, go ahead, please, and thank you very much to give this talk in today.
Okay. Thank you for having me here. It's a pleasure to speak in front of all of you. So I'm going to talk about this work that is called on phenomenological parametrizations for the luminosity distance of gravitational waves. It's a pretty long title, so don't feel overwhelmed. So it's kind of straightforward to the point. So I'm going to start by talking about the main problem that this work, I don't know if some of you are familiar with, but it's points to solve some or to analyze some of the dark problems of the universe. So I'm not gonna go deeply into general relativity, but I'll here know about the issues that we have studying the cosmological, the universe at large scales, cosmological scales. So we have the dark problems, dark energy, dark matter. Um, we need to solve them. So all the scientific community goes beyond trying to explain this with a lot of ways in a lot of manners. So I'm my first attempt to approach this problem was to go deeply into modified gravity. So the modified gravity, it's a way to modify the general relativity by the um, the modification of the Lovelock theorem. So we have additional fields, we break assumptions of the general relativity. We have so many ways to modify the general relativity equations in order to explain the dark sections of the general relativity. So we are here. We have a lot of theories, different theories. Everyone can have their own theories by modifying something from the general relativity schema. So we need a way to shorten this kind of multiple options we have. So the gravitational waves can lead us to some clues to discard some of the models or to point towards more mm, a very pretty better model that we can have. So how can we do that? So after we obtained this signal, the GW170817, we have new data to have to in 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 our sites. So the speed of propagation of the gravitational waves, it's now we know it's the speed of light. So with this data, we can discard a lot of the modified gravity models. Just with that measurement, we discard some of the models. So we after that measurement, we just remain with some of the models. We don't have no all. So this was a first motivation to explore the gravitational waves and to have more information that we can obtain from the gravitational waves to discard some of the models. So that's what I said. Just say the propagation of gravitational waves can give us information about the universe and its mysteries. So we need to analyze this propagation in different waves. So the first thing we need to do is obtain gravitational wave equations from these models of modified gravity. I say previously that we have a lot of different gravitational modified gravity models. So from each of them, we can obtain his gravitational wave equations. The equations of the gravitational waves, as all of you may know, are obtained by perturbation theory from the general relativity. So we have the field equations from the modified gravity scenario. We perturb the metric. We linearize the field equations. We applied some gauge conditions, and we obtain the the wave equations. That is pretty straightforward, as all of here may know, be familiar with. So we can, for each of the modified gravity, obtain gravitational wave equations. These equations can be the difference between the wave in general relativity and in modified gravity can be summarized in this term. This is the equation in a Friedman Robinson Walker black background, so in a lambda cold dark matter model. But if we consider a modified gravity model, we have this term, that is this delta, that depends on the conformal time. All of the difference between the propagation in general relativity and the propagation in the modified gravity wave uh, are summarized in this term that appears on the damping term of the wave. So we can focus on analyzing this term, that is this delta. So what is this delta? This delta is related to two different observable in the universe. That is the luminosity distance, as we usually know, the electromagnetic luminosity distance, the one we measure of the objects in the universe, and the luminosity distance of gravitational waves. Thus, this is a term that is related to the luminosity distance of electromagnetic waves by multiplying this coefficient, this scale factor in both scenarios. So this luminosity distance in the gravitational wave scenario and the electromagnetic scenario are different just in the case that this delta is considered. So it's just in the case of the modified gravity scenarios, as we can see in this equation. Also, it's useful to define this term that is chi, um, that is the coefficient of these two luminosity distance, the gravitational wave and the electromagnetic luminosity distances. These two, the coefficient between these two is related to the delta, the factor that I previously mentioned, and is related to the delta in this manner. So this is unobservable because it's the relation between these two of them, and is more related to the data. So this delta, the existence of it, so the value being different from that, I need to correct this one, implies difference in the distances. So, but no, does not imply the existence of this delta does not tell us about there is one of the models, so it can be any of them. But we can analyze its properties. So if analyze the properties of this function, we can discriminate more, even more of them in the amount of models we have. We discriminate a very big part of the models by measuring the speed of propagations. And if we analyze this function in a very more deep way, we can discriminate even more models, and that can lead us or give us clue of where to look for modified gravity models. For example, we begin and in my doctoral thesis, we analyzed this set of models that are more related to the Einstein scalar gas bonnet gravity. So these are kind of models that are modifying the general relativity by adding scalar fields. Those are a family of models, very big ones. So we focuses on these four. These four consider different scalar terms and other things. So for every one of these models, we obtain it as I previously mentioned, the gravitational equation and the delta for each of them. So I didn't add it to the presentations due to the time issues, but that's what we did. For every model of it, we obtained an expression of the delta. So in order to assess be more general in our assumptions, we use parametrizations. As we physics know, the use of parametrization it's a common way to be more general and explain features that needs to be in the functions that we study. So we analyze some of the parametrizations first proposed in this article, Belgasem et al. 2018. This is the article where the team that made the first measurement of the gravitational waves. So they propose some parametrizations. These parametrization that they propose are these three, and every one of the deltas has its analog in the high chi space. So every delta has its chi. So this set of two are parametrizations that are proposed in this article. So what we have with these parametrizations proposed, we have very different behaviors for this parameterization. So we have a model, this delta these black dots are the model of modified gravity, and we have some different parametrizations, and we try to fit them to the model to see if the parametrizations are better to fitting certain modified gravity models. So what we see here is that some of the models, some of the parametrizations are predefined or predetermined to be explanatory of very specific kinds of models. So we can't use parametrizations to look a plethora of models or very several models or several different models. So we need to choose specific parametrizations for specific models. For example, this delta 2, it's a parametrizations that points to modify gravity models that begins at a fixed point of expansion that it is the zeta point. So it's not for very big delta zeta. So, and this is the behavior in the chi space. As we can see, this is a more, they can be seen as more well-behaved functions that fits better to the model. But the difference is that here we have a cumulative effect. So in the zeta equals 0 zone, it doesn't seems pretty different because of it is a coefficient between the two luminosity distances, and this is the chi is a coefficient between two luminosity distances, and in zeta equals to 0, c equals 0, they are practically the same function. So that's why they all begin in 0 in 1 point. So what is the focus of this work was to add a different parameterization that can be more general and cover more of the models of modified gravity. We did some mathematical works to have an expression that can be more flexible between any of the models that we consider, that can be a model that can begin in a fixed point or that can diverge in this c equals to 0. So we did an expression, we made an expression that can do that. The cost of this parameterization is that in the other parameterizations proposed by the article that previously mentioned, they have just two free parameters that were these two, the n and the chi 0. So in this parameterization, we have three that is the r, the n, and the chi 0. So we did the same test, and we obtained that this model fits better to any kind of model as we previously assumed. We have the axis or parameterization or new parameterization, and this two is the model that has a fixed point at the c equals 0 zone. So the parameterization can mimic that curve. And as you may know, we made a chi-square analysis. So to see how the model behaves and with a quantity. And we obtained very good results comparing to one of the better parameterizations that proposed earlier in the article. Also, we made a test, the R-square test, that penalties the model or for parametrizations with the amount of free variables we gave to them. So we use 3 and the other parametrizations used to. And even if we penalize the model, the parametrization with that, we we still have very good results. So in conclusion, this work represents and we did some numerical treatment to the data, to the models to obtain the gravitational wave equations. We focus on an analysis that is to obtain the delta, and the delta can lead us to some information that we may not have been considering for the gravitational waves that can lead us to some clues to discard gravitational wave, modified gravity models for the general relativity that can explain the dark zones of the cosmological studies. So it's all for me. I don't know if you have questions. Thank you for your time.
Thank you very much, Andrés, for your presentation. And if any have some question, go ahead, please.
Hello, everyone. I don't know if I am the first one.
Yes, you are.
My question is, if we think of the gravitational waves as a wave, it should characterize by uh, a wavelength, and the luminosity wavelength is affected by the cosmological redshift, cosmological factor parameter, the A. When
Scale
I
factor, you
saw,
mean?
yeah, I'm sorry, a scaling factor. When when I saw your presentation, you showed us the the distance, the difference between distance of gravitational waves and emission or luminosity distance. What are the physical difference between them?
Yes, but if you mean we the lumin the name implies that they are very related. So they both are luminosity distances. What we can we can say about it is that every object, for example, the collision of two black holes, it can emit both of the or a collision of two stars. They can emit the two signals, the gravitational wave signal and the electromagnetic signal. For both of them, we can measure the distance from where the event occurred. The gravitational wave signal, as you know, the gravitational waves propagates through the space-time, and the space-time it's affected very affected by the but it is described by the general relativity, not affected, described. So the equations of the general relativity that describe it can be affected if we consider a modified gravity scenario. In that point, they are different, and they are considerably different. And that's where the delta enters and explains that difference, or at least not explains, but takes account and accounts the effects that are present in it. So this is the main difference. One propagates through the space-time, the other is the electromagnetic wave emitted by the source. Both have a source, and it is for a single event we can have both. And if we measure differences, we can associate them with the existence of a delta function that points toward a modified gravity model. So that is the point of the delta.
Thank you very much. I understand very easy. Thank you.
Okay, thank you, Nicolas. And anyone who has another question? If not, I have a question. In the slide 11, Andrés?
Slide 11.
Yeah. Which in the equation 7, do
Equation
you
7,
use
okay.
a potential here?
Yes.
And do you have the form? Which potential do you use, or how do?
See, yes, I don't have it in the slides, but I have it in the article. So it's a very simple potential that we considered in order to assess more characteristics of the scalar field. So we focus more on the difference between the scalar field, that is this function, I don't know the Greek letters in English, but I don't know, chi, I don't know. But this function is the scalar field that appears in the equation. The action of it is the scalar Gauss bonnet. So the potential, I don't have it, but it's pretty straightforward, and it is the same for 4 of the models. So I owe it to you, so I can, if you give me some minutes, I can share it.
No problem. It's okay. Another question is if you think that you can obtain a comparison of your result with a real detection of gravitational wave. For example, the GW 17817 in your first slide.
Yes, what was, can you repeat it, please?
If with your analysis, it's possible to obtain a gravitational sigma with your model. To model, if you can model gravitational waves with your model. For example, do you have this distance, and the gravitational waves depend of this distance?
You mean this equation? This is the equation for the waves in a
Yes.
modified gravity scenario.
Yes, but when you have the solution depends of the distance. And the distance also has a relation with the electromagnetic distance has a relationship with the gravitational signal. No, you don't, yes, this depend of this distance have a comparison with this, but both of them can be put in the solution of gravitational waves, and you can model it.
Yes, model, do you mean the delta
So,
modeling?
no, the age, I mean the age. Okay, if you
This
want,
perturbation term, yeah.
yes.
Okay, so I mean, we just consider some of the models that the affectation of the propagation appears only in this term, that it is if we see this as an oscillatory equation, this is a damping term. So this damping term appears in these kind of models that are the modified gravity models that only have the affectations in this term. We didn't consider in this term because this term affects directly with the speed of light, with the speed of propagations. And if we affect this term, we have models that propagates in speeds lower of the speed of light. So that is pretty constrained by our observations, so we didn't consider models that affected this term. So every of the models of modified gravity seems to have different equations for this perturbation equation. Also, as you may know, there are plenty of different models of modified gravity. Even some of the models consider like a coupling between the metric and the gravity. So these models aren't considered, but they are. We are working towards to consider these models. So I don't know if I answered your question, but
Yes, it's okay. Thank you, Andrés.
thank you.
Okay, then thank you to Andrés for his presentation, and now we will continue it with Alexander, please. Can you share your
Thank
screen?
you. Thank you for
While
having me.
thanks to you, Andrés. I will to mention the CV from Alexander. Alexander, he holds PhD in physics from Federal University of Juiz de Fora in Brazil, a master's degree in astrophysics from the University of Valparaíso in Chile, and a bachelor degree in physics from UPN in Colombia. His research focused primarily on gravitation, cosmology, and particle astrophysics. In 2023, he participated in the discovery of low-frequency stochastic gravitational wave background in the NanoGrav collaboration. He's a member of the collaboration LISAC, the Cosmoverse, and LAA EPCAP. He is a reviewer and a guest editor for high-impact journals such as Nature, MRAS, Physical Letters, APJC, and a postdoc, and Universe, among others. He is currently a postdoctoral researcher at the University Federal of Brazil and an assistant professor of mathematics of the UDC in Colombia. Thank you, Alexander, and go ahead with your presentation, please.
No, thanks to you, Claudia. You can see my presentation?
Not very well, but we can
What
see
happened?
Now I can see it. Now you share full screen?
Yes? Okay?
Yes.
Okay.
Yes, here. Thank you.
Okay. Okay, thank you by this opportunity. Thank you to the organizers by this very important initiative in Latin America. Today I will talk about the fundamental physics with gravitational waves. Fundamental physics have many things, but I will concentrate in some topics that I working on. Okay. Let's go. The idea of outline is to do a very short introduction, theoretical framework, methodology, and results, and final remarks. Okay. And then we can go to the introduction. Some theoretical progress with the standard model of cosmology. We can enumerate some of them. For example, coincidence problem. Why the density of dark matter and dark energy today are the same order of magnitude? The fine-tuning problem. Why is the cosmological constant so small and can change of sync? And quantum vacuum energy density, why the calculate value of the cosmological constant from observation is 120 orders of magnitude larger than calculated by quantum field theories. Here we have a great motivation for study alternative models to dark energy, that dark matter, or in general modify Einstein equations, modify gravity or alternative models to gravity. But in general, for me, it's very important look to the quantum gravity. Is very important in this moment for us. You have some proposals, for example, for the first problem, we have alternative models to dark energy. Between them, I work in with different cosmological models that can solve or this problem. Modify gravity, FR, FT with torsion, massive gravity, tensor vector scalar, many theories, and the last holographic dark energy is very interesting for me, but in general in the community is no don't have acceptance, don't have is no more important in the community in general, but holographic principle is very important for solve some topics between gravity and quantum systems. Okay, with the alongside the theoretical problems, we have observational problems. All we know these cosmological tensions, the Hubble tensions and the semi tensions between others, and the tensions is when or happen when we calculate these values, the Hubble parameter or the rate expansion rate of the universe, and when you use information of the early universe, for example, from CMB, that is the most precise data set that we have at the moment, you obtain a very low value of Hubble parameter, and when you use data sets from the late universe, you have a high value of this parameter, and you have attentions between this value and this value. We need to solve this tension. Proposals are, for example, systematics or new physics, for example. And you have the same problem with the sigma parameter that have in account the scalar perturbations, and you have the same problem. Okay, these problems are motivating for searching new physics for us. Okay, but you can review, you can go to this interesting, it's a white paper that the Cosmoverse Codsation initiative, where you have many cosmologists in this initiative. And in this white paper, we speak about the systematics and fundamental physics too. Okay. Okay, let's go to the methodology. In methodology, we will concentrate our efforts in gravitational waves. We have here the spectrum of gravitational wave when you have the spectrum in frequency and in strength of amplitude of gravitational wave. You have in principle three different sectors. In the first sectors that you have LIGO, Virgo, Cagra, Geo, and many others detectors. This works in high frequencies, but when you go to intermediate frequencies, you have a LISA detector, laser interferometer space antenna. And when you go to the low frequencies or very low frequencies, you have the work to do by nanographs in an international pulsar timing arrays. You can look here the sensitivity curves of different experiments, different detectors, and you have two different type of signals that, for example, in nanographs, the main objective is supermassive black holes. In all these spectrum, you have different compact binaries in different size and mass. Okay, you have here in LIGO astrophysical black holes, for example, or you have two neutron star. In general, compact binaries. Okay, here we have different detections. For example, you have two main plots that we obtain the different information about the events. You can take different information in time domain or in frequency domain, but in versus to a strain or amplitude that is proportional to amplitude of gravitational waves. You have three events: GW5914, LBT, and GW501226. And you can see here the gravitational wave profile in time domain, but you have the same information in a space of frequency domain, where you look how evolve the signal in this space, and you have to this curve of sensitivity of the detectors. You have to también you have to information. You have to also information of polarization states that in general relativity are 2 plus and cross. And you have here one view of the velocity and separation for astrophysical objects, where you can see how separation in time goes down and velocity goes up. Okay, here I have the GW17817. We will short review of the first multi-messenger event. You have Virgo space, and you have the information too from the Fermi satellite and integral instrument in this satellite. See how the signal of gravity and more or less 20, I don't remember, 60 after that.
Alexander is gone, I think so. Wait for him a moment.
The merger. Okay. The merger is something complicated. What didn't it need a reconstruction from numerical relativity, and read down is other charter one explore spectroscopy. with quasi-normal modes. And we are concentrated in this first part of the spiral. Okay, this event is a great motivation simulation. In our simulation, we consider
Claudia, I think we have to postpone his talk to another meeting.
with this simulation, we do these words. In this word, we use this simulation to put constraints on the delta parameter. Delta parameter is a parameter of one model, interactive dark energy model, where in this model you convert, for example, dark matter in dark energy, and this parameter delta is the interaction parameter, and you can see using different data sets like cosmic chronometers, supernovae, BAO, H-Nolico, and gravitational waves, you can see that we have departures from lambda CDN that is in this plot is here in 0. And in this other word, we use this simulation to put constraints on the speed of gravitational waves. But we can prove too the ability to constrain parameters like Hubble parameters or or matter parameters between others. Here for us is very important this constraint from LIGO. This constraint from LIGO that established practically that the speed of gravitational wave is the same of the speed of light. They use this distant luminosity for this result, but we use this distant luminosity in Hondersky modified gravity, where with the simulation we obtain this constraint for Einstein telescope and the SIGO, and you can see here the difference. Here is the 10 to the minus 7, 10 to the minus 16, and you have 10 to the minus 2, for example. Okay. This group in China nanographs gravitational waves of 0.87c, and they use this data set that is data set from nanographs. This data set is very, very, very interesting. And a nanograph, the vet of nanograph are supermassive black holes, but in this case, in this world, we use in nanograph for nanograph data, we use pulsar timing array technique, where we have more or less a data set of more or less 100 pulsars, and with these pulsars we constrain in the same way. We use this data set that is the pulsar Hughes and Taylor. We use this data set to put a constraint on the velocity of the gravitational waves that you can see here, the estimate. Our estimate is 0.95 C, but at the same time, we put upper limits on the mass of graviton. That is very important for us to know if the graviton have mass or not. And we obtain other parameters of this pulsar, like the period, the mass of the binaries, eccentricity, and delta parameter that is related with the mass of graviton. And we obtain similar results like in other papers. Okay, in the same paper, we review other part of the spectrum of frequency, and you can see the same three parts: low frequency, intermediate frequency, high frequency, and ultra high frequency detectors that is very important to have in account this initiative, ultra-high frequency gravitational waves from the Center of Theoretical Cosmology, Stephen Hawking. I think that Odilio belonged to this initiative. And for me, it's very interesting, this relics primordial gravitational waves background. When you have in this thin curve, one model of massless inflation, but when you give mass to graviton of this model, you can obtain this thick curve. And you can see that in the first case, the up-to-date detectors is impossible detect this signal, but when you have a mass in this signal, you have the possibility to detect. And the other signals that are very interesting are, for example, cosmic graviton background. That is very interesting. Why this is possible in the near future with detectors in this zone. It's possible to detect this cosmic graviton background, but had serious consequence for inflation too. And we are studying this consequence with the proposal detectors. These detectors are very interesting. Each instrument works different from nanographs. You have a technique of pulsar timing arrive. From LISA and LIGO Virgo Cagra, you have laser interferometers, and you have here magnetic resonance. And you have explored many phenomenological fundamental physics, like inflation, stress species, inflation, effective field theory, scalar perturbation, prehearing, oscillation, phase transitions, that is very interesting. Cosmic string is very interesting. Metastar string, gases textures, and cosmic graviton background too. This is new physics. This is fundamental physics or exotic physics. How do you like? We want the multi-messenger approach, where we have in this moment, the photons of the CMB, but we want relic neutrinos and relic gravitational waves for to know the early universe. And in this case, I will promote the LISA detector, laser interferometer space antenna, and we can obtain information from this these events. You have first in the first part dynamical friction. You have the final part parsec problem, gravitational wave emission, and something like a recoil. Why the environment, these supermassive black holes or massive black holes have environment. This environment is very, very, very complex. Okay. We do another simulation, but in this case is from standard series from LISA, and you can see that the extension is up to redshift 10, and you have three different populations. You have the light, not the light, all depend of the model of environment. But with this information, we use Gaussian processes or neural nets to do this inference, and you obtain from the simulation this relation, and you obtain finally age, the whole parameter, for to do what? For to do, for example, one exploration of the variation of the physical constant, like a fine structure constant, or like the Newtonian constant. You can see that they depend of some parameters like B, but depend of the matter and depend on the age. If we have age here, you can put constraint here, but we have two data from this variation of a fine structure constant. It's very important for us. And you have to, we are very interested in review the Lorentz-Bell-Leighton dispersion relation of gravitational waves. And here, Younes et al. To do very interesting work. Why this part is the parameters of Lorentz Bell-Leighton, and you have different possibilities like a double special relativity, extra dimension theories, Horowitz theory, theories of non-commutative geometries, many things about that. Some upper limits, for example, with the mass of gravitons, and in the parameter A, that we can put constraints in this relation dispersion. And the idea is to do a joint analysis in machine learning using, for example, data from H-Nodely code, that is data from gravitational lens. And you have here, for example, in this plot, you have this equation that is diametral distance. It's a dimensional diametral distance, but you have this diametral distance where you have the information of the different gravitational lengths, and you put here in this term, you can note that difference of times depend on the graviton wavelength or wave contour length of graviton, and the frequency of emission, and depend on the parameter A, the Lorentz Bell-Leighton parameter that have length weight, relate length weight, and you can note how, for example, the phase term is affected by these terms. Okay, we are working on, and for the future, you have here the representation of the constraints with Einstein telescope, LISA, or International Pulsar Timing Array. In more or less in 2013, you have these possibilities, and the idea is obtain information from gravitational waves. We need to be more precise. Thanks.
Thank you very much to you, Alexander.
Thanks, and excuse me.
Several work that you are doing. And if any have a question, please go ahead. Okay. If no, I have a question, Alexander.
Yes.
The models that do just show are modeled with a, okay, I saw the pulsar, famous pulsar, but for example, the last slide that you saw, you have a redshift between mass, and the mass is about what object? The mass, or is the mass of the what? And the last slide.
Yeah. I know. Is the mass of a binary system.
Okay. Then you use mass. Yes,
Yes,
in the last word, yes.
this is like
Yes.
this is the mass of the binary system. You have here, for example, supermassive black hole, intermediate, for example, NRISE, mass string radio mass spiral, and you have here astrophysical objects, neutron stars or black holes. But in general, for example, we want to know if you have hierarchical process or by merger, one merger, two merger to produce a supermassive black hole is one question in this moment. And the other question are, for example, the primordial black holes are very interesting too.
Okay, you show also results about the cosmological constant. What do you think about the tension on cosmological constant? If I understand well, maybe no. You have different numbers in different words for the
Cosmological constant
yeah.
is lambda CDM. Okay. Here in this plot, you have an alternative model to lambda CDM. This model is namely interactive dark energy model. When you have interaction between dark sectors, in this case between dark matter and dark energy sectors, and you can convert one in each other. How happen this is very complicated. You have information that you have an interaction, but what type of interaction result here is we need to go to microphysics to explain this, okay? By a moment, we can show that the deviation is considerably more than 3 sigmas. And this is one evidence, no, the unique evidence. For example, this it show us the other evidence that the lambda CDN is not preferred by the up-to-date cosmological data. We have some certain that the dark energy is dynamical.
Okay, thank you, Alexander.
No, thanks to you.
And thank you for your presentation
Okay.
also. And if there are no questions, we can finish with this day presentations. Thank you very much again to Andrés and Alexander for the talk, and see you next month.
See you.
Bye.
Ciao a
Thank you.
todos.
Sure.
Thank you for
Bye-bye.
having us. Bye.